In this video, we're continuing section 5.4 on log properties, and we're going to focus on domain situations involving log properties. So what happens to functions when we use log properties, and how we think about their domains. Okay, so I want to get right into an example where we find the domain of each pair of functions. So there's going to be two functions here. The first one is ln of x squared, and the second function is 2 times ln of x. So the problem asks me, well, are the two functions equal to each other? And then, well, if they're not equal to each other, then solve for the x values where they are actually equal. So maybe they'll be equal to each other for some x values, but not all x values. So find the x values where they are the same. Okay, all right, so a few different parts to this question. So the first part asks me to find the domain of each of them. All right, so if I have this first function, ln of x squared, when I have a domain problem, I want to think about restrictions. And for this function, I see one restriction, which is I have a log. So the thing that's inside of it, which is x squared, well, that's got to be greater than 0. It can't be equal to 0, right? Because the thing that's inside of a log cannot be 0, and it can't be negative. It's actually got to be strictly bigger than 0. So no equal sign. Okay. And, well, for this inequality, x squared is greater than 0, right? So I'm not allowed to just square root both sides of an inequality. That does not work. I kind of have to use logic to solve this inequality. So if x squared is bigger than 0, there's only one value that I can plug in for x that would break this inequality and make it not true. And that's if I plug in 0. Like if I plug in 0, I get 0 is bigger than 0, and that's not true. But otherwise, if I plug in a positive, I get a positive number here. And if I plug in a negative, when I square it, it's still positive, and that's going to be bigger than 0. So the only bad value is if I plug in 0. So I get to just say, well, x is not 0, if I use a little bit of logic there. Okay, so my domain, I'm going to write D for domain, is everything except 0. So that's negative infinity, comma 0, with the parentheses, union 0 to infinity. So it's everything except 0. That's my domain in interval notation. Okay, and now let's compare that to this function g of x, which is 2 times ln of x. Because I would say at first glance, it looks like they should be the same. Because if I use the power rule on this and move the 2 to the front, it seems like that just becomes 2 ln of x. But let's see if that checks out when I find their domains. Okay, like will they have the same domain? Okay, so for this function, I see one restriction. Again, I have a log, so the thing that's inside of the log, which is x, well, that better be bigger than 0. But this inequality is already solved for me. The x is already isolated. So I'm ready to just write down my domain now in interval notation. So this domain is a parentheses at 0 onwards to infinity. Just everything that's bigger than 0. So I'm going to box it. That's my domain. Okay. Right, because with this one, there's no squared on it like I had the first one. So I'm not going to be allowed to plug in negative numbers because I can't take a ln of a negative number. Whereas with the first one, if I plugged in a negative, the squared will get rid of it and make it positive, and then we're good when we plug it in. So these two functions have different domains. So as a result, they're not the same function, which is weird, right? Because the question I now have is, wait, if we use the power rule, like I just talked about, aren't they the same? Like, wouldn't the power rule just let me move the 2 out in front to get 2 ln of x? So the answer to that is I am kind of deliberately kind of glossing over one important detail of using a log property, which is that both sides, both logs must be defined. All of our logs have to be defined in order to use a log property. Okay, and these two logs, ln of x squared and 2 ln of x, well, for them to both be defined, when does that happen? When are they both defined? Well, it happens just when x is bigger than 0, because the second log is only defined when x is bigger than 0. So as long as I limit myself to just plugging in positive numbers for x, well, then the two things are in fact equal. I can put an equal sign, but only if I limit myself to plugging in positive numbers. Again, because if I plug in anything negative, well, this thing will be undefined. I'll have a problem here. But with this other one, I'll be totally fine because the squared will get rid of the negative. Okay. All right. So I can use the power rule, but only if this inside thing, the x, was bigger than 0, because that's what I need for this log. Okay. But then a question I might have is, we saw above that the domain of ln of x squared is, well, everything except 0. Everything except 0. So is there a way now, to tweak the power rule somehow, adjust it so that it would work for everything in the domain, like everything except 0, including negative numbers? And the answer is yes, I can. Yes, but carefully. Yes, but carefully. So, okay, so how do we do that? So I'd love to be able to do it without having to restrict myself to only being able to plug in positive numbers. So here's what I want to notice. Let's say I had ln of 9 squared. Like, I know that if I do the power rule on this, the 2 will come in front and I'll get 2 times ln of 9. But is there another way I can sort of think about that? That'll help me with my problem. So if I do move the 2 to the front, what then happens to this number when I get rid of the squared? Well, one way I can think about that is, currently we had 9 squared, but then to get rid of the squared, I have to square root it. Okay, and well, what's the square root of 9 squared? Well, the square root of 9 squared is just 9, right? Because that's the square root of 81, and the square root of 81 is just 9. Okay. All right, so that seems a little bit like unnecessarily complicated. Like, why am I doing that? Why am I writing that in this way? It's because that'll be very helpful to me when I have a variable here, and it's unsure whether I have a positive number or a negative number in the x. So if I pull the 2 out in front of this, and I do the same thing, I'll have ln of, I got an x squared there currently, but when I remove this squared, I end up square rooting the thing that's there. But what's square root of x squared? So I got 2, and then I got ln. Oh, square root of x squared. Right, we saw stuff like this way back when, in like the second week of our class. It's not just x, right? Recall that it's absolute value of x, right? The square root of x squared, I'm going to highlight it. The square root of x squared is absolute value of x. So why was that? Remember, so like if I had square root of x squared, remember that no matter what I plug in, even if I plug in a negative number, the squared is going to wipe it away. So this whole thing ends up being non-negative. This thing is definitely non-negative. So if I were to just say, well, don't they just cancel and give me x? Well, the problem with that is this answer choice could be negative. This could be negative. Sometimes if I plugged in a negative number for x, it's negative. But this one won't be negative if I plug in a negative value for x, because the squared. So as a result, these are not equal to each other. So how did we fix it? I'll put a bullet point here and another bullet point. The square root of x squared, well, I need an absolute value around the x. And now that guarantees a non-negative output. Guarantees a non-negative output. Okay, so the ln of x squared, what does it actually equal when I do the power rule in general? Well, it's 2, and then I get ln of, I'll put it in parentheses, absolute value of x. Okay, and this is going to now work for all x values that are not 0, including negatives, because this, another way I can think about it is, well, now the absolute value will let me plug negatives in and wipe them away. Because this side already has a way of wiping away negatives. The squared wipes away the negatives. Now this side has a way of wiping the negatives away as well. It's the absolute value. So let me write that down. Over here, the squared, that squared gets rid of negatives. And on this side now, I have something that gets rid of them as well. It's the absolute value. The absolute value gets rid of negatives. Gets rid of negatives. Again, because before I put the absolute value there and I just had this, the right-hand side didn't have a way of getting rid of negatives. And that made the two sides different. Okay, so I'm gonna highlight this. I am going to highlight this. ln of x squared in general is actually 2 times ln of absolute value of x. I need that absolute value there So now that their domains match. And now both sides have a way of wiping away negatives. Okay. All right, let's do another example. All right, let's say I have now ln of x to the third, and my other function is 3 times ln of x. So seemingly, these functions appear to be the same, like if I were to use the power rule and bring it to the front. So let's see if that indeed is the case here. So I'm going to think about restrictions. Let's find the domain. And I see one restriction for this function, right? The inside of the log, which is x to the third, that's got to be greater than 0. That's got to be greater than 0. And again, I'm going to use logic to kind of solve this inequality. I'm going to use logic here. Let me just write the word logic above that arrow. Even up above, when I did this one, let me just write the word logic here. I use logic to get that. So if x to the third ends up being positive, what does that mean about the number x that I was plugging in? Well, the number x that I plugged in has to be positive. It's got to be bigger than 0, right? Because if I plugged in 0, I would get 0 over here, and 0 is not bigger than 0. And if I plugged in a negative number in for the x, and then I cube it, it becomes negative, and that's definitely not bigger than 0. So the only type of number that would work is if I plugged in a positive number for x. So that's my logic to get this. Okay, so let's write this domain in interval notation. So I get parentheses 0 onwards to infinity. All right, I'm going to box it. And I think that makes sense because if I look at this function, this power is an odd power. So it's not going to wipe away any negatives. If I plug in a negative into this, it's going to stay negative because of the odd power. And that's bad. That's not allowed in the log. Okay, let's find the restriction for this next function. Well, the thing that's inside of it, so there's one restriction here, the thing that's inside of it, which is x, well, it's got to be bigger than 0. Okay, but this one's already isolated, so I'm ready to put this in interval notation. My domain is parentheses at 0 onwards to infinity. It's just everything bigger than 0. All right, let's let me box that. That is my domain. Okay, so this time the two functions have the same domain. So because these domains are the same, the power rule does just work as I expect it to. So I can say that ln of x to the third equals 3 ln of x. Like these two functions are in fact equal to one another. So here f of x does actually equal g of x. Okay, which makes this one different than the previous example. Okay, I might ask the question, wait, does this kind of check out with this explanation I was giving about the power rule with x squared? So let's investigate that. Let's investigate that. So if I look at ln of x cubed, and I bring that 3, that power out in front, I'll get that 3 out in front, and then I'll get ln. And when I bring that 3 out in front, what I'll be left with is x cubed. But when I bring the 3 out in front, I end up cube rooting the thing that's inside. I end up cube rooting it. Okay, but when I cube root x to the third, the cube root of x to the third is actually just x. And the reason for that, I'll put a bullet point here. The cube root of x to the third, I don't need an absolute value this time around it, is because if I have an odd power and an odd root, it's totally okay for this to be negative. This can be negative. Like if I plug in a negative number for x, the odd power will keep it negative, and it's totally fine to take a cube root of a negative number. It'll just be negative. So if I say, wait, is it just x? Yeah, that makes sense because if I plugged in a negative for x, this whole thing is negative. But this whole thing is negative too. This can also be negative. So I don't run into that same problem that I was running into square root of x squared, where that was definitely non-negative, but x could have been negative, and then I needed to fix it with an absolute value to make it non-negative. Okay, so it does kind of check out with this more technical explanation of when I pull that power out. Okay. All right. So what I want to do is I want to take a look at one more example here. So let's take a look at one more example. All right, so this is on the next page. And so first, what I want to do is I want to give you an opportunity to try this. So I got these two functions. I got one log minus another log, and then g of x is just one big log function. So I want to give you some time to find the domain of each of these functions. So just finding the domain of each of these. So pause the video for about 4 minutes, maybe 5 minutes, to try to find the domain of each of these. Okay, so you first want to find the restrictions and then try to get the domain. Pause it in 4, 3, 2, 1. Pause it, and try to find the domain. All right, so hopefully you did that. Hopefully you paused it and tried it. So let's talk about it together. But real quick, before we do, let me just briefly kind of go back to this previous problem and try to give another kind of, intuitive explanation for why I don't need an absolute value this time. So if I have ln of x cubed, and then I got 3 ln of x, well, they are in fact equal, because if I have x cubed, I can't plug negative numbers in at all, because the odd power will keep them negative. So we can only plug in positive values for x. Okay, and that matches with what I have over here. Like with this x, I can only plug in positive numbers for this x as well. Okay, so that's matching already on both sides, so we don't need anything to adjust that like we needed with the x squared. We needed the absolute value to make sure both sides, we were able to plug in the same thing on both sides. Okay, all right, let's go back to part C here. So finding the restrictions. So for this first one, well, I see 2 log functions, so there's going to be 2 restrictions. The thing inside of the first log, which is x minus 7, that's got to be greater than 0. And the thing inside of the second log, which is 2 minus x, that also has to be bigger than 0. So these, well, how do I solve these inequalities? These are both like the easy type of inequalities. They're linear, so I can just isolate the x. I can isolate the x, so I'll just move this 7 over. That'll give me x is bigger than 7. All right, and the other one, if I move the x over, I get 2 is greater than x, which is the same thing as saying x is less than 2. Okay, so I'm going to plot these both on a number line. So number line here, and a number line here. So let me put a tick mark at 7. And on the bottom one, I'll put a tick mark at 2, which is smaller than 7. That's why I'm drawing it to the left of 7. So based on this first inequality, there's no equal sign, so open circle. And I'll shade in the stuff bigger than 7. And the second one, there's no equal sign, so open circle. And I'll shade in the values that are less than 2. Okay, so I need both of these restrictions to be true. So I need the first number line to be satisfied as well as the second one. Okay, I want just the x values that satisfy both of these conditions. Okay, so when I see that word and, well, that means an intersection. That means an intersection. Okay, so now I'm going to form the number line where I put this together, where I take the intersection of these number lines up top. So when I take the intersection, recall, I just want the values that satisfy both. Sorry, I just want the values that are satisfying both. In other words, just the values that are shaded in both of the number lines. So what x values are shaded in both? Well, if I look at some values here, they're only shaded in the bottom one. They're not shaded in both. What about the stuff between 2 and 7? Well, they're not shaded in either one. And the stuff to the right of 7? Well, that's only shaded in the top one, not the bottom one. So there's nothing that's shaded in both of them. So because of that, my number line is empty. My number line is empty, which is a little weird. And that means my domain is nothing. My domain is nothing. What that means in terms of these logs is, no matter what number I try to plug in, at least one of the logs will end up having a negative number inside. That's unavoidable. Like if I try to make this one positive inside, well, the other one ends up being negative, and vice versa. So the domain here is nothing. Okay, so let's see if the same thing happens in this function g of x. Because at first glance, it seems like, well, maybe the function is supposed to be the same, because we have that log property that says, well, if you subtract 2 logs and the bases are the same, you just get 1 log and you divide what's inside of the 2 logs, because that's what this is. Okay, but let's actually see if the domains will be the same. All right, so for this function as well, I see 2 restrictions. So I see a denominator. So remember that my denominator, 2 minus x, well, that's not allowed to be 0. Okay, and if I rearrange this, we get that x is not equal to 2. But there's another restriction because I have a log. The thing that's inside of the log, which is the whole fraction. So the whole fraction, not just the top or the bottom by itself, the whole fraction has to be greater than 0. Okay, so I have this inequality now to solve. Ooh, but this is one of the more complicated inequalities. Like, it's not just one where I can isolate the x, because it's not linear and it's not quadratic. This is one of those inequalities where we got to do the cut point method. But luckily for us, it's already in a form where we can just write what the cut points are right away. All right, because one of the sides is 0 already. It's already factored as much as we can get it to be. So what are the cut points? Well, from the denominator, I get 2, right? Because that's what makes the denominator be 0. That's my undefined cut point. And then I also need the things that make the numerator 0, which is 7. That'll make the whole function be equal to 0. Okay, and now I form a number line. I form a number line. All right, and I put a tick mark at my cut points, 2 and 7. And then any of the factors I see either on the top or on the bottom, I make a row for them. So there's a row for x minus 7, and there's a row for 2 minus x. I separate them with a line, and then where I have my cut points, I put vertical lines to make columns. Okay, and now I got to make my sign chart. So with x minus 7, if I were to plug in anything bigger than 7 in for the x, anything bigger than 7, like 8 or 9, well, it ends up being positive. And if I plug in anything smaller than 7 in for this x, like 6 or negative 1, it'll end up being negative. Okay, what about for 2 minus x? Well, I know if I plug in 2, it becomes 0. If I plug in anything smaller than 2, like 1, it's positive. If I plug in anything at all bigger than 2, like 4 or 10, it's going to be negative. All right, cool. So now we put them together. Now we put these signs together. So if I have a negative times a positive, that's negative. Here as well, positive times a negative, that's negative. But a negative times a negative is a positive. Okay, so I got the overall, those are the overall signs of this fraction in each region. Okay, my inequality says I want it to be greater than 0. That means I want it to be positive. So I'm going to be shading in the positive region. I'm deliberately leaving the cut points blank for right now because I got to think about if they're open circles or closed circles. So remember that a cut point that's undefined because it makes the denominator 0, and that's 2. 2 is the undefined cut point. Well, if you plug that in, it'll make the denominator 0, and that makes this whole fraction undefined. And then the inequality is just not going to be true. It breaks the inequality because one side is undefined. So the undefined cut point is always open. Right? We've seen that a number of times now. For the other cut point, the one that comes from the numerator, well, I could plug it into my inequality to see if it works. So if I take x equals 7 and I plug it into my inequality, over here I'll get 0 divided by something. 0 divided by something. And that's greater than 0. That's my other side. But 0 divided by something else is just 0. So I get 0 is greater than 0. Oh, but that's not true. So I'm going to put a sad face. 0 is not greater than 0. I'll put a sad face. So because it did not work when I plugged it into my inequality, it should have an open circle as well. Now, I would only shade it in if it works when I plug it into the inequality. Okay, so my domain for this one, my domain is 2 to 7. That's my interval with parentheses on both. Okay, so these two functions, which seem like they should be the same if I use my log rule, well, they actually have different domains. So as a result, the two functions are not equal to one another. They're not equal to one another. Well, for which x values are they equal? Like, are they actually equal sometimes? Well, to make them equal, both sides would have to be defined. Both sides would have to be defined. And when does that happen? Like, when are both sides defined? So are there any x values that work in this domain and work in that domain? Unfortunately, no, because the domain of this one is nothing. So this happens for no values of x. They're actually equal for no values of x. Since the left-hand side, that's this one, the left-hand side has no domain. If there was some domain here, then I would look for, well, which x values work in both. What x values satisfy both of these intervals? Okay, so as we'll see in later videos, when we solve examples in which we use log properties to solve an equation, we'll just have to be careful when we solve the equation. What that will result in us doing is having to check for extraneous solutions when we use log properties. That's going to be one of our big takeaways from this.